Everybody. Sticking to the end, we have the best part for the end. We have two outstanding talks from across the state lines. So we're going to start with Mike Shatruck from FSU, and then Neutron from Clemson in South Carolina. And so we are going now in the world of magnetic materials or more exotic materials. So of course, that's the best part of this workshop. And we are very glad that our colleagues came to visit us today, and looking forward to Mike's talk. Take it away.
Thank you very much. I don't know, my title is very generic, so I'm not going to talk about that. Because I didn't know what to talk about, so it took me time to figure it out. But I will talk about magnetic materials, not so much about applications, but I will talk about applications of Pauli diffraction. Scattering for studying magnetic materials. Is it too long? Okay. So I'll tell you two short stories. And the first story will be about the story of Pandora's box, which is in a modern interpretation is called a can of worms. And the kind of moral of the story is trying to show why we should apply new methods to old problems. Sometimes I think we kind of go to new things all the time. We don't look back at the older materials. It could be very interesting if we look carefully at that. Of course, we have new methods that can really open some things that we haven't been able to identify 20 and 30 years ago. One of such old materials is manganese oxide, which is very well known in neutron diffraction communities, while the first magnetic structures were determined by Schul and Wolin at Oak Ridge National Lab. And of course, what happens in this case, we have Pauli diffraction below the magnetic ordering temperature. The antiferromagnetic arrangement, antiparallel arrangement of spins breaks the symmetry of the crystal structure, and you see this additional peaks that pop up in the neutron diffraction pattern. You can then integrate it, find the magnetic structure of the material. And so in particular, manganese oxide is really a prototype antiferromagnet. It shows doubling in the unit cell in all three directions, because half of the manganese spins in the 1-1-1 planes with one plane and the next plane they go the other way. It's alternating antiferromagnetic structure. And one would say, well, everything's known about manganese oxide, but actually it's quite surprising. There are still very important papers coming out. So these two PRL papers that came out in the last 20 years first established that magnetic moments of manganese are oriented 1-1-2 to bar direction, and that was done by combination of neutron scattering and reversible color modeling. And then the paper 10 years later actually applied magnetic PDF function to look at this J1 and J2 exchange coupling ratio, and actually turned out that this exchange coupling is similar between the nearest neighbor and next nearest neighbor, the exchange. Okay, so again, like there are a lot of things we can do with these materials that get fundamental size and magnetic structures, magnetic exchange. And when we approach this problem, the reason we wanted to do it because we were studying more complicated ternary, quaternary manganese chalcogenides, and we had some observations that magnetic moments were quenching by manganese sulfur and manganese selenide bonding, which we thought was due to covalency. And then I asked my student to just look at binary chalcogenides as reference materials. And when he did that, he discovered that there are a lot of conflicting reports about magnetic moments, manganese sulfide, manganese selenide, manganese telluride. And so we just decided to re-examine the magnetic structure of these materials to have reference points. So we asked Oak Ridge to give us a couple of days to study 3 magnetic structures. That's where all the stories start. And so manganese sulfide we recently published. I'm not going to talk about that. And there was another paper that came out about the same time about this magnetic structure. So the moment there is about 4.3 for magneton. Now we're pretty well established that. But manganese selenide is quite interesting because it shows transition between sodium chloride, cubic type structure, hexagonal nickel arsenide type structure, really close to room temperature, 160 to 170 Kelvin. And in fact, manganese selenide hexagonal, when it forms, it's already magnetically ordered, while manganese selenide cubic isn't. There are quite a few mistakes in the literature attributing structural phase transition to magnetic phase transition, manganese selenide, which obviously is quite a big blunder if you see that kind of statement. So what we we'll be doing with these materials, in particular, we're applying inelastic neutron scattering to look at that exchange interaction between nearest neighbors and next nearest neighbor manganese atoms, and even next nearest neighbor. And inelastic neutron scattering, very brief, simple introduction for many, I guess, for people who don't do this regularly. What we're doing here, we're looking at the momentum and energy transfer correlation diagram. So above ordinary temperature, we typically see this elastic band with zero energy transfer, which is essentially our neutron diffraction pattern. But below the ordinary temperature, you start seeing these excitations that develop and emerge and become stronger, more and more pronounced, which correspond essentially to magnetic exchange between magnetic moments. So now we have energy transfer between the material and incoming neutron beam. And we can integrate this, we can model basically this neutron scattering data to extract exchange directly extract exchange constant in our magnetic materials. So again, if you're interested in this, you can look at this paper. We have quite detailed analysis there for manganese sulfide. And we've been able to look at this J1 and J2. And one thing, for example, we found that in manganese sulfide, J2 is almost 4 times stronger than J1. And the reason this happens because you're removing now manganese atoms further apart, so you're decreasing this direct interaction, but you have very strong super exchange across the sulfide bridge due to strong covalence in this bond. So you have quite a lot of spin density in the localization of manganese sulfide, and that really strengthens the exchange between manganese atoms across this 180-degree bridge, sulfide bridge. Anyways, when we start looking at manganese selenide, here's the magnetic patterns, the neutron diffraction patterns of 3 manganese chalcogenides at 4 Kelvin, so they all are ordered here, and we're quite successfully managed to fit this manganese selenide pattern by using a 2-phase mixture of alpha manganese selenide, sodium chloride type, and beta manganese selenide, which is nickel arsenide type. So this works quite well. We got the magnetic moments. You can see an interesting question, for example, is why magnetic moment in a cubic structure is substantially smaller than the hexagonal structure. Something we're trying to look now to examine theoretically right now. Then we decided to go from here to inelastic neutron scattering because we thought, okay, we should see excitations from both of these phases. We're going to extract, model them to get the J values like we did with manganese sulfide. And here what we get. So here's manganese selenide, and this are for comparison to the inelastic neutron scattering patterns from manganese sulfide, manganese telluride. And what we see in manganese selenide, what we can do, we can take, for example, a section of this, integrate this data in some key range, and look at our peaks that we obtain, and then try to fit into our model. So this is essentially just a cut from point 1.97 to 3.07, somewhere in this range, whereas we just start to integrate the data and try to fit them. And so what you see here, you see 3 peaks. And just briefly, one of these peaks actually comes from this band, and this band corresponds similar to the band we see manganese sulfide, cubic manganese sulfide. Okay, so this is manganese selenide. Okay, and then we see the second band with higher energy, and this is correlated to the band we see in manganese telluride. But then we also see the third band, and whatever we tried to do, we couldn't fit this third band to anything. So we see 3 different bands in manganese selenide excitation spectrum and that's neutron scattering. And so that's what we call opening the can of worms. Okay, so now the question was, are we going to really figure it out? We'll just say there's some impurities. So Judy Clark, who was doing this project in my lab, she really started getting very interested in this. And well, we decided since we see this on neutron, we should be able to see this X-ray diffraction. So we see this in neutron scatters. Maybe we can see it very soon. And so she's gone to our X-ray instrument, and she did it on single crystal synergy S. So this is perfect time for me to give this talk. If you listen to an excellent talk that John just gave about single crystal instruments used for foundry X-ray diffraction, I don't need to introduce this anymore. Two people here changed my life, Sean and John. Because Sean persuaded me to buy synergy S, and John told me it was a really good instrument. And so literally, if you guys didn't pursue me to do this, we wouldn't get these results, and we wouldn't find that we wouldn't make the discovery. I'm going to show you a few slides. So Julie started looking at this conversion, right? And she clearly saw two phases, hexagonal and cubic. And what I'm showing you here is percent of hexagonal phase, just extracted by fitting the two-phase X-ray, arbitrary diffraction mixture. It was done on very small amounts on microscale sample on a single crystal diffraction loop. And what you see when we cool down at 1 Kelvin per minute, so what we do here, we cool down at 1 Kelvin per minute, we stop, we record a 45-second pattern, cool again, and we just take patterns very, very quick. And what you see is we can build up to 20% of hexagonal phase. And we start seeing it around 180, 200 Kelvin, not before. So then I told her, well, go slower. Okay? Of course, you know, your lab mates will love you for taking so much time on X-rays, but it's okay. So she started going 0.6 Kelvin per minute. And now she can build up to 50% of hexagonal phase. But not more. Okay, so whatever we're trying, we cannot get full conversion to hexagonal phase because it's very, very slow transformation. And then I asked Julie to just stay here, okay, just thinking about kinetics. Maybe we stay at higher temperature, we allow this conversion to go faster, and maybe we can build up completely, complete 100% hexagonal phase. Mind you, we don't see that third phase. We only see two phases in all these patterns. And so she's done it. So we decided, oh, we're just going to flash directly to 160, so we don't have to waste time on cooling. We're just going to put our instrument to 160. We're going to immerse the sample at that temperature and just stay there and start building up our hexagonal phase. So she's done that. So she flash cooled the sample to 150 Kelvin. And at 150 Kelvin, staying for 6 hours and just maintaining the sample there, you can see we're only building very little of hexagonal phase. These are black peaks here. Our hexagonal phase in gray, this is not the greatest choice of colors, but you can see the very, very small amount of hexagonal phase merging. It doesn't really grow as you go up in time. And then we went to 155. Okay, let's increase the temperature to let the system convert. Again, nothing really happens. We're staying, it's a very small amount of hexagonal phase. And then we went to 160. To kind of encourage the conversion. And now we don't see hexagonal phase, but now we see something new popping up. We went to 165. Now this third phase becomes dominant, right? So we are observing the third phase just by this weird flash cooled experiment in a very narrow temperature range. And I cannot put like 200 plots here, but I can tell you when you go to 175 or 180, I don't know exactly, you don't see that phase anymore. You only see Q. Okay, so there's this 20 Kelvin window where you can generate the third phase, which we think is orthorhombic. And right now we have scheduled experiments in synchrotron to figure out the structure of this phase, high resolution data. Well, what's happening here, right? There's this wonderful movie with Orson Welles, Third Man. So this kind of reminds me that we've seen this phase, but we have no idea what it is, right? And of course, this is very classic transformation. You'll find many, many papers, not theoretically or kind of on the fingers here, without anybody really seeing that intermediate phase. I think some people who do nanoparticle conversion did see some kind of orthorhombic phase during this magnetic phase transition. So what we do is we're just shifting our AB layers to ABC layers, vice versa. We go from CCP to HCP packing. In this case. And of course, what we expect happening is just based on the conversion from this structure. This structure, you have to go for some orthorhombic intermediate. If you look at the groups, subgroup relationship in space groups, you'll have to go through that route and convert the structure to orthorhombic. And so now we really hope that with high resolution synchrotron data, we'll get the answer really soon to what's happening here. But in the meantime, what we did, we tried to do X-ray pair distribution function analysis. And Emil Boston at Brookhaven recorded this total scattering pattern. And so this is fit to cubic structure, 300 Kelvin. The fit is excellent all the way to 50 angstrom. And there's no any problem with PDF. But then we decrease the temperature. Right? So here's PDF, fit is cubic at 10 Kelvin. We get only 34% agreement factor. But when we fit as the two-phase mixture at 10 Kelvin, the agreement factor is much better. But I'm cheating here a little bit because I'm showing you the agreement factor only to 10 angstrom, in this case, 20 angstrom in this case. If you actually look at the larger scale, right, you see that the higher distances really give you really mediocre fits. So there's no fit at all, huge deviations. And we can plot essentially this, the agreement factor as a function of R. And what you see, we have pretty good fit up to about 10 angstrom, and then it starts getting much worse. Okay, so our hypothesis here is that essentially what we have this kind of reconstruction, structural reconstruction, where our hexagonal cubic phase converts to hexagonal phase and propagates to some kind of interface. And there's basically, this gives us some sort of a characteristic domain size measure for this transformation. So you see it be kind of moving with this characteristic domain size of five atomic planes in an hexagonal structure. So it just keeps propagating through the crystallites. Okay, and this kind of fancy image that Emil built to explain what's happening here. So anyways, I think we'll be able to nail down this phase, this orthonomic phase with some experiments we're planning. But it's really difficult because you need to use very small amount of sample to rapidly cool it to specific temperature. And so we send the sample to Melee and ask them to do specifically what we wanted, but they didn't manage to do it. So they could not obtain that phase, and we went again to synergy and we obtained that phase again. And I'm pretty sure we're not doing any chemistry on synergy under X. There's a lot depends on the really very exact experimental problem. Okay, so I still have time, right? To tell the second story. Okay, so the second story will be kind of related in a sense, in the philosophical sense. So this is something chemists we heard from the DARPA program manager. They told me you don't need to make any new materials. My group makes a lot of materials, and we like making materials and then studying them. Right? So to me, this was really demotivating, and I started thinking about just closing down. And so what I'm trying to tell you today is that why we should continue making. Try to persuade you that they are needed, okay, because it's boring to study the same stuff again and again. And so the second part, I'm going to talk about kagome lattices, and that's more of a new directions, right? New materials, not old materials. And of course, kagome lattices in just are aesthetically beautiful, and they are really great test beds for looking into phenomenal spin frustration, where you cannot satisfy pairwise antiferromagnetic interactions on an odd number circuits. Right? So if you take classic example of a triangle where you put two antiparallel spins, then on the third side of the triangle, you don't satisfy that condition, and then you start getting some weird effects, spin canting. The lack of magnetic ordering to very, very low temperature, of course, hot research on spin liquids, quantum spin liquids that's related to that frustration. One thing my students never see, they never see me in business attire, and they never see me showing this cloth because I hate it. But I think in this case, this could show you really well this new life that's been pushed into the area of kagome materials. So this is a publication. I just typed kagome lattice, counted the publications for those, and anything you do will give you this kind of trend. Okay, that's really stupid. But if you look at kagome metals, you can already see qualitatively that this boost in kagome lattice studies mainly comes from kagome metals. And if I normalize and use science here, you can see that even better. But if you look at studied materials, there are just very few formulas that describe everything that people are doing right now in kagome metals. And kagome metals is a really bad name because really what they mean is kagome-ferromagnetic metals. Some kind of magnetic ordering, not just be metallic. And so these are things that are really hot right now. If you look at iron 3-2, that's probably the best characteristic of this situation, because iron 3-2 was first made, I think, like in 1907. But if you look at the Web of Science, I think 90% of papers in that compound came out in the last 5 years. Okay, somebody finds something interesting, out of sudden, of course, this is like whale in Iraq. Fermions, there's still argument on the whale of the Iraq, and there's a very interesting bad structure, and that comes from electronic frustration to get on not only magnetic frustration, electronic frustration on kagome lattice demands. Okay, that's kind of the reason for this interesting physical behavior. So our question was kind of looking at this. I always tell my students, I'm not going to study things that 200 groups in physics study with better expertise. I have no idea what's going on there. I can just make. So I always tell them, let's make something where we can actually do our work and not worry about publishing next year, but actually do kind of nice column analysis and learn some. And so we got attracted by this 166 structure because it's pretty simple. It's there's 3 elements, not 2. So we can vary things more, right? We have more handles to manipulate. We also like when we can throw in 4F magnetic electrons, which I will not show today, but that's kind of the plan. We're going to put some other things there instead of just yttrium. But pretty much everybody's focusing right now, many groups focus on this yttrium manganese 6 structure. We don't. Okay, so this 166 has kagome layers of transition metals, and then they are separated by electropositive elements and main group elements, electropositive elements here. And there are a lot of structures with this composition, and they slightly different symmetries, but there are a lot of opportunities. And so what my group likes to do, we like to find different crystal structures, different symmetries, different magnetic properties, go in there and see what happens in the interface between those two regimes. Okay, so for example, if you look at yttrium iron 6 germanium 6 and yttrium cobalt 6 germanium 6, they crystallize in very similar structures. I can superimpose this and this. I didn't do it. My students, I don't know how to do it. Yeah, so there's small distortion in the iron-containing compound, but structures otherwise are very similar. And yttrium iron 6 germanium 6 antiferromagnetic is very high magnetic ordering temperature. The cobalt-containing compound doesn't show magnetic. And then the question, of course, we ask: can we achieve a ferromagnetic phase here? Can we just make ferromagnetic kagome metal in this German? So the reason we think we can do that is because if you just look at the very simple idea of ferromagnetic metals as elemental 3D 3D metals, right? We start with scandium, so we have the Fermi level quite below with respect to this high density of states in the Fermi level. But when we get to chromium, we're approaching this large peak in those, and we start seeing antiferromagnetic ordering. When we go to iron, cobalt, and nickel, now this Fermi level crosses this peak, and that's where we start seeing ferromagnetic ordering. And that essentially follows this idea of Stoner and other people who formulated the criterion that if you take the exchange constant multiplied by the density of states at the Fermi level, if this product exceeds 1, then you should expect ferromagnetic ordering, itinerant ferromagnetism. And this basically just comes from mean field theory of magnetism. What we want is take the material that's antiferromagnetic and raise its Fermi level to start crossing then the dose peak and hopefully satisfy this other criterion. There is also, from a chemistry perspective, there is a slightly deeper insight in this situation. So we can plot this crystal orbital Hamilton population function, which is really nice to describe in this paper by Jankowski and Landrum. So I call it Jankowski's criterion of ferromagnetism. And so in scandium, the Fermi level is pretty low, so it crosses the bonding states. So positive here means bonding, negative means anti-bonding. Negative electrons are pushing apart, don't want to reform bonds. But as you fill up your D band in chromium, you start crossing the non-bonding states, and that's a characteristic signature of antiferromagnetic ordering, according to Jankowski. And then once you start crossing anti-bonding states with negative COHP, then you start seeing ferromagnetic ordering. Okay, so that's kind of the way we think about the possibility to modify metal from AFM to FM state. So here's the density of states for yttrium cobalt 6 germanium 6 and yttrium iron 6 germanium 6. Remember, this is antiferromagnetic. You can see similar to chromium, we have the Fermi level very close to the peak. If you do COHP analysis, you'll see that there's non-bonding states at the Fermi level for iron-iron interaction. But in cobalt, we went too far. When we crossed this peak, we filled up with these D states, we see ferromagnetic behavior. So what will happen if I push my Fermi level to the peak? We expect to see ferromagnetic ordering. So Vicky Lee, my current graduate student, she did all this like range of substitutions, going from pure iron compound to cobalt compound with step of 1. And so you see a very nice 166 structural pattern. But if we're going to zoom in on this characteristic area right here, it's very clear that we transform yttrium iron 6 germanium 6 from orthorhombic structure to hexagonal structure around this 3 to 4 range. Okay, so the question is, does that structural transformation correlate with magnetic properties? Becomes very interesting now, and indeed it does. So for larger iron content 543, all these phases are orthorhombic. We see antiferromagnetic ordering, and for the phases that become hexagonal, we see ferromagnetic ordering with quite different magnetic ordering temperatures. Now we can also look at magnetization. So for antiferromagnetic, we should just see linear magnetization as a function of magnetic field. This is done in 5 Kelvin, so you can see these iron-rich phases have just very simple linear magnetization. But for cobalt 4 and cobalt 5, we start seeing this kind of ferromagnetic-like behavior. We don't think these are collinear ferromagnets. We think they are candid ferromagnets, ferrimagnets, if you will. And that's actually what we're looking for. We want to find structures with really weird spin textures. And so we think this will be good candidates for seeing that. But if you look at the magnetic phase diagram that we now plot, we kind of have this AFM region with gradually decreasing ordering temperature, and then we generate ferromagnetism. And then, of course, this what we like to call now magnetic phase boundary that we want to investigate in more detail. And so Vicky did very careful work going small steps. You can see different kind of magnetic curves. I'm just showing you this to show that these are not antiferromagnets. Okay, this all shows some kind of ferro or ferromagnetic type ordering. Now we have pending experiments in Oakridge to look at the magnetic structure of a couple of these. And we kind of have this very nice area now where we have ferromagnetic kagome-like. And I'm sure we'll be able to generate them with other systems of this sort by using the same approach. So this immediately opens the playing field for kagome-like because you can put 4F moments there, as I mentioned, instead of yttrium, we can start throwing in other things and really vary the chemistry, the structures, and the types of magnetic spin textures you might achieve in the ordered state. Okay, so with that, I will just stop and I'll acknowledge Julie, who did the first part of this work, and Vicky, who worked on the second part. And funding mainly came from MnSe. Oakridge has been very generous with lead time for us. And Ovi Garlio is our longtime collaborator for neutron scattering. I also showed the result from Emil Bozin on PDF, and they've been super helpful as well. And thank you very much for your attention.
Mike, talk. Any questions? So let me ask first about the can of worms. So you have a spectrum with 3 bands. So are you assigning 1 to? So does it mean there's the orthorhombic in the 2 other phases, or what's the scenario?
Right. So we think the third band is in that 3rd phase, but we don't know how that phase. What we don't understand is why that phase forms during regular cooling in neutrons, and we cannot form it with the regular cooling in PDF analysis. So we just puzzled completely about that. Is that, I guess that's what.
So this was measured at 5 Kelvin in powder can, or traditional?
It was cooled to 5 Kelvin pretty quickly in vanadium can. Yes, there was nothing very special about the cooling procedure. It was repeated twice, and he saw that very consistent. Of course, the amount of sample is much larger. It's huge, but we have no idea why it shows up in the neutron pattern. It doesn't show up in the powder pattern. So we like really positive. Well, it's sort of it does show up in PDF, right? Because we see that the coherence, that fit, and we think that fit is because we don't have the 3rd phase. If we introduce the 3rd phase in the PDF fit, we probably will fit that all that noise. That's our expectation.
So maybe just to follow up on this, so one thing I'm interested in looking is so if the structural coherence is limited to whatever it is, 15 angstrom or 20 angstrom, the spin excitations will behave very differently at high energy than they are at low energy. Essentially,
that's right.
the top of the band is a very local spin excitation, and the spin wave cone is a long range. So do you actually see like the spin waves going to low energy and having some coherence, or do you essentially just see flat modes that tell you, okay, your system is kind of just a local, it's just a lot of local spin?
Yeah, that's a good question, and I don't have the answer because I didn't look at the low energy.
But I think
Yeah,
I think one thing to confirm it might be to look at that.
Yeah, that's a great
coherence,
idea.
magnetic coherence.
Yeah, that's a great idea. Very good.
Like, so very nice talk, but I was actually just going to follow up on the discussion you were having with Martin there. I wondered if the difference between the two experiments might be just the sample prep. And I don't mean the original synthesis, but if you're doing X-ray work, PDF, student grinds it well, they're worried about large grain size. You've got a 6 millimeter vanadium can, just chuck it in. So I wondered if there were issues of nucleating something because something had been more heavily ground. We've seen things like that.
Maybe. Maybe. I agree that probably 3 grams they don't grind as well as 50 milligrams. That could be true. I think a lot of that also depends. My feeling is it mainly depends on the structural coherence and on the way they cool. And because we haven't, as I said, we sent the sample to APS, we told them very specifically what to do. And they couldn't see the phase, and then they described me how they did it. And I told them, it's not how I told you to do it, right? It's different. So now I'm going there in March or wherever they're going to schedule, and just making sure to do it exactly what we do. Because it has to be very, very fast. And also I think what happens, I really think that's like creates some kind of stress, right? And that space is generated with the initial interfaces due to the stress. But then with time, so even like at 170, 175, I showed you guys the 24 hours. She left it over a weekend and it disappeared. It went back to cubic. Third man, I'm telling you, it takes time, right? So it just disappeared because then your structure slowly anneals, right? And goes back to cubic. Just never pushes enough to go to the second. No, sure. Don't be shy. You can ask.
Yeah, I was just thinking about how you
Cool. Warm. Right.
very user.
We did flash cooling and then warm. But we never tried to cool back. So just to see if it's going to show up again. Because my guess is if you warm, if you go back to cubic and you start cooling, you will not see the things. Because you cannot create the strength. Right? And it also kind of follows from our just cooling from room temperature. But we never tried to go to like 175 when we see the phase, and then start cooling down slowly before it disappears. To see if cooling down slowly, you can start pushing to its end. So I don't know. There are a lot of things you can do there. Just people want instruments, right? So if I have my own, John will tell me that I need to buy a new one. We just, yeah.
What's up there for
You mean the sample, just the quality of the sample, the change during storage? Oh, I don't think that would go. I mean, they're so stable and they look very clean. Neutron basically made a huge gram, multi-gram sample, send it off. I don't know, a month maybe. Takes time, but I don't think. Never say never, but I really don't think that's the shot. Because the powder pattern, when you do powder, it just looks very clean and all impurities are the only background. And we store them very well. We keep them in argon filled dry box and never expose them.
Any other questions? All right. Thank you so much, Mike.